Our goal here is to go after all the design stages of chip design, from data path and architecture design all the way to sign-off.
7, 8, 9 years ago, when an individual chip about this size, a semiconductor chip at the leading edge, would already cost $100 million to design. So then the key insight becomes, wait a minute, that chip is also, in some sense, just placing logic in a small physical footprint. So maybe the same algorithms can be applied there.
Like right now, the market is there's internal teams of hundreds or thousands of people, and it still takes a couple years.
You could do it faster, you could do it better, and you could do it end to end.
There was some interesting, the curved shapes of the placements were very strange to the physical design team. No human expert would generate a layout with this organic shape.
But nature would.
We see the company in 3 phases. In phase 1, our goal is to accelerate the chip design process. In phase 2, we can be a platform for chip design for many other companies, like the robotics company, the self-driving cars, the AR, VR. They are going to benefit from specialized custom chips that serves their models at significantly faster speeds or better energy efficiency and all that.
So Act 3 would be...
Hi everyone, I'm Guru Chahal and this is the Investment Memo, the show where founders reveal the stories behind their businesses and how they will shape the future of their industries. Today I'm joined by Goldie and Azalia Mirhoseini, co-founders of Ricursive Intelligence. Anna and Azalia revolutionized the field of chip design with their groundbreaking work on AlphaChip, the approach Google used to design 4 successive generations of its flagship TPU. Ricursive is the evolution of this approach, using AI to compress years of manual work into weeks and unlock a new era of custom silicon. Today, we'll talk about why chip design has become the bottleneck to AI progress, how Ricursive's approach changes the rules of EDA or electronic design automation, and how the recursive loop between AI and hardware may very well bring about a Cambrian explosion in this field. Anna and Azalia, welcome to the show.
Thanks for having us.
It is such a pleasure. I'm so looking forward to this conversation. One thing I can promise you, it's very different from anything we've done so far and probably what you've done. Because what we're going to do here is not just go behind the scenes of your business and your ideas and who you are, but actually behind the scenes of our business and how we do it. So I want to share with you something very, very special. This is a copy of the investment memo that we wrote internally for the partners here at Lightspeed. I'll also give you markers if you want to highlight anything. This is probably the first time you're seeing a document like this. You make decisions that could be in the hundreds of thousands of dollars to hundreds of millions of dollars, sometimes billions of dollars on the back of the research we do, on the back of the work we do. And then one of our jobs is to bring all of that information up to a level where we can make an investment decision. And a lot of that goes into these. So here's what I was thinking for today. We'll maybe divide up our conversation into 4 or 5 big areas. Walk me through, how do you come up with this idea for, let's use AI for chip design, for semiconductor design?
Yeah, so we were working on a project related to placement, but it wasn't chip placement. It was related to how we map a neural network that's really large and doesn't fit on a single, say, GPU or TPU device across multiple devices or even multiple nodes. We had a research project on that. That was the start of our collaboration, and we showed there that we can use reinforcement learning to take care of this mapping and partitioning task such that the model runs fast or in high throughput, different metrics that we want to optimize for.
Right. Would one way to think about that placement logic be, imagine a jigsaw puzzle? Like, how do you fit things? A jigsaw puzzle that you can fit things in multiple ways. And so what's the most optimal way to fit different blocks together? That's sort of at a highest level, that's sort of a physical placement of what goes where. The problem you're working on, and the key insight was, hey, we shouldn't have to do this by hand.
Yeah.
We can get machines to do this.
Yeah, exactly. I think in this case, it's really nice because the reward signal is so clean. So you figure out, okay, how I place all these jigsaw pieces, and then I just run it.
Right.
See how long it takes. It takes less than a second to do a forward pass, backwards pass parameter update. And that's the reward signal that matters.
That's the definition of good. So you know right away, and the machines are so much faster than us at experimenting, running, because you don't have to sit there, yeah, this is good, this is bad. They can just calculate the reward signal very, very quickly.
The other nice thing was the velocity of that initial project. So we had this idea of how to do this hierarchical RL. We wrote all the code, we ran all the experiments, and we wrote the paper in 3 weeks. And then we're like, okay, what can we do next?
That's pretty interesting. So you're taking software at the time and you are using AI and reinforcement learning to build a system that can more optimally run that software across.
Exactly.
Yes.
What's the next? How do you get from there to semiconductors?
Because we're like, this is a graph placement problem.
Right.
So maybe there's tens of thousands of nodes placing onto maybe 8 GPU cores or TPU cores. What's something that's even larger scale, harder, and
Higher
more
impact.
impact? Yes.
Yeah.
At the time, I mean, we're already talking about a world, 7, 8, 9 years ago when an individual chip about this size, a semiconductor chip at the leading edge, would already cost $100 million to design. So then the key insight becomes, wait a minute, that chip is also in some sense just placing logic at different sort of in a small physical footprint. So maybe the same algorithms can be applied there.
Yeah.
What did you do next?
At the time, Google Brain was this awesome place. They would allow people to propose these bigger projects that were called moonshots.
Right.
And if they were accepted, that means that you get a little bit more visibility, maybe a little bit more resources, not a whole lot, but it just gives you that kind of a flag that you can say, hey, we are a moonshot now. And we can go and talk with potential partners. In this case, we went to the TPU team at Google because that was the most exciting kind of application chip for us. And that was kind of, we were at the time still excited about this recursive loop. So we wanted to use AI to help design of these AI chips, the TPU chips at Google. So the Moonshot kind of became a foundation for us to start this project little by little. Like for a while, it was just Anna and I. Yeah. And we were kept trying to show results, work with the TPU team because they were not coming from the AI world. And at the time, there was just less kind of trust or appreciation of AI. The process took a while. Yeah. It took a lot of meeting with them, showing results, walking them through our process and the type of results we can get and the type of improvements we can kind of achieve. And that helped us kind of break into the TPU team and their process.
At what point did it become really interesting for executive leadership as well? They're like, oh, this is a true moonshot. This is really interesting.
I think Jeff was involved from the beginning.
So one of the senior most leaders at Google is already supportive of the project because he's also seeing what you're seeing. Like, hey, this could be really dramatic.
He was a co-author of that device placement paper. So we had been working with him already. Right. They had this Moonshot program and we were thinking maybe we should have a Moonshot on AI for chip design. And we thought maybe Jeff would find that interesting. So we were kind of drafting this email together because we thought maybe this is too crazy sounding. Let's carefully write this message. And then while we were drafting it, we got an email from him saying, let's do a Moonshot on AI for chip design.
Oh, I love it. That's amazing. And that then leads to the AlphaChip paper. It leads to actual utilization of the technology you build in production for use cases as Google designs it. Most people know this now, but Google is a they have an incredible semiconductor program. After NVIDIA is probably one of the most at-scale deployed AI accelerators on the planet today, the TPU team. And you've had a direct impact, and the technology has a direct impact on that over the years. When you left, by that time, this was in production and being used. And so you'd gained that trust of the semiconductor team and they'd gotten used to. Was that a big sort of journey? Or once they got it, was there an aha moment where they saw a particular design and they're like, oh my God, I would have never thought to do this, but this is obviously better.
I mean, there was some interesting, the curved shapes of the placements were very strange to the physical design team. No human expert would generate a layout with this organic shape. But the metrics are better.
Right. But nature would.
I think it's more
and
natural.
In some sense,
more natural.
AI is sort of emulating years of evolution in some sense, and just compressing that into a smaller time frame. So we might I certainly like everything at right angles, but AI is just learning and running those experiments. And so at some point, that project became a larger team. You're no longer there. Is that project now supported by its own team and it's just a way they do things?
It continued. It was used in 4 successive generations, including the latest one.
Right.
And I guess the other part is that it expanded beyond TPU.
Oh, interesting.
So this method is used in Pixel. The Axion CPU team, Google has this mono repo, right. Google 3, anyone can access code from any team. And they just found our code and they ran it and they generated layouts and they taped them out for the Axion CPU. So
that has to be very satisfying.
Yeah, that's very satisfying.
Yeah. But I mean, I love this, right? Because So much of what we do here in Silicon Valley, and certainly in the startup ecosystem, is built on the shoulder of giants. It's built on experience, whether these are open source projects or projects like these. It's tremendous amounts of experience that you gain. So now you've built this incredible sort of technology and platform internally where Google is able to use AI for chip design. It's still constrained. It can only serve a relatively small constituency within Google. I'm sure at some point you must be thinking about how do we make this bigger, which then leads to Ricursive. But before we get to Ricursive, I want to draw your attention to one additional thing. If you look at one part of the memo right there in the thesis section, the first one, what we were talking about was, we said, hey, this technology has very compelling validation. Like, it's not just two researchers, amazing researchers saying, we think we can use AI for chip design. These are researchers who have done it and they've learned. And so there's just natural right to win in this market and an accelerated product design cycle that you can have because you have that learning. And so that was the first part. The second part I want to dig into is chip design is a fairly complicated process. This is not, going to Cloud Code and saying, hey, design a chip. This is many, many things. This is thinking about the system level. What are the requirements? What does this chip need to do? Then writing the code for it. And then this critical phase of physical design, which is not present in software, which is, okay, where do the individual capacitors and circuits go? How is everything sort of tightly packed in this little piece of silicon? Mm-hmm. Why is that a great starting point for AI? Why did you want to address that and not maybe, let's write very long code with this or, some other aspect of chip design?
As a company, and our goal here is to go after all the design stages of chip design, from data path and architecture design all the way to sign-off. So that is going to be our focus. The very first project that we started at Ricursive was physical design because it was that was the area that we had worked on before at Google, and the team that we have built around this is experts in physical design optimization. And this is one of the hardest stages of the process and a long pole in the design. So we want to go after the long poles first, and physical design is a long pole along with design verification. So we have to address all of these, and we are going after all of these stages, but we are starting with the physical design as the first component.
I was going to say it can be very risky. Like, we've heard about some custom AI chip startups where they were delayed by a year or more, and they could not close the layout. They couldn't manufacture the chip.
That's right. So I'll just read up from the memo. It says physical design is a compelling insertion point because chip design is a multi-step process. It spans the overall system level design, the RTL design, which is writing the code, and then physical design. And so what's the point of doing all of the other work, doing the system design and writing the code if you can't fit it? If you just physically can't manufacture it, what's the point? And so this is sort of like an architect building the plans for a house, and then a contractor looking at it saying, this is not buildable. Like, the house is like this. It's not possible physically. Like, a structural engineer and a contractor have to sit down and figure out how we're going to build this. And so that phase is the hardest one. And one thing we found in our research was this is not the kind of stuff that the existing foundational models are focused on. This has to be unique IP that you have to create.
Exactly.
So it's a hard problem. You have existing experience in it that's been proven to work. There's very limited competition. None of the giants in the field are focused here. So what are unique opportunities? That's why I really like this as an insertion strategy. But I do want to dig into that point you made, Azalia. So it's not just about physical design. I mean, your ambition is much more. Let's talk a little bit about that. What are the different phases of the company as you build things out?
Yeah, so we see the company in 3 phases.
Okay.
In phase 1, our goal is to dramatically accelerate the chip design process. And that is going after all of the components, beginning with the long poles and the physical design. But we are going to, again, go from architecture design all the way to sign-off. We are going to accelerate and automate this entire process. In phase 2, now that we have accelerated and automated the process, we can be a platform for chip design for many other companies that right now cannot make their own chips because they don't have a chip team of like hundreds to thousands of people, right? So we want to let these companies be focused on their application layer and other kind of aspects You can think of them as like the robotics company, the self-driving cars, the AR, VR, all of these kind of application companies can be focused on that. But given the scale of these companies and how the field is moving, they are going to benefit from specialized custom chips that serves their models at significantly faster speeds or better energy efficiency and all that. And we want to be the platform that designs the chips for them. So they don't have to worry about the chip design.
I really like what you said, Azalia, because in some sense, you're turning the entire market on its head. Traditionally, and we wrote this down in the memo as well, traditionally the semiconductor market is actually really interesting. You require tremendous amounts of expertise, lots of incredible engineers, hundreds and hundreds of engineers, hundreds of millions of dollars to produce a chip. It takes so long and so much effort that you want to produce a chip that can run all sorts of workloads. So you have one x86 and it can run everything. One NVIDIA GPU and it can run all sorts of AI. That is the right approach when it's that expensive to build these things. But what if you could change that dynamic where we could easily design hardware that is customized to run just my software? Then the only thing that matters is at what scale do I want to run that software? And any company that's going to run software at scale probably now deserves their own custom silicon. That's the big vision. That's the big vision in this phase 2, which is so exciting that you can just fundamentally make this more accessible. In fact, we looked at the market numbers. We'll dig into those in a bit. And then we basically threw away the market numbers because our view was you're going to expand the market by many, many, many times because you're making this much more accessible. Sort of like what vibe coding is doing in the software engineering market. Instead of 25 million people writing applications, we could very well have hundreds of millions of people writing software applications. So why not the same in hardware?
So Act 3 would be, if we have this capability to quickly design like highly performant chips, why not use that ourselves? And why not build our own chips, train our own models and co-evolve them? And then we could serve intelligence at a cost or a capability that no one else could possibly match.
And that's where the idea of recursive comes from, this sort of recursive improvement between a co-design of software models and hardware at the same time.
Yes.
Which is incredible. It's really interesting, right? We spend so much time designing these incredible models today, and then we try and force put those into existing hardware. Mm-hmm. If instead it could be a co-design process, that could be incredible. And it actually marries those first two things you did, where placement in the software domain and then placement in the hardware domain, and now the whole idea comes together. And that's really exciting. Then you have something that's very different than just changing the semiconductor industry. Then you have truly intelligence, unparalleled intelligence at unparalleled efficiency, which is really intriguing. I'm going to draw your attention to one more thing in the memo. We'll go to, in the thesis section, which is about the market itself. It says structural opportunity for disruption. And I've told you, I really enjoyed looking at the market structure. I actually started with EDA tooling. I said, what is the structure of the market? And it turns out, there's a couple of very, very large incumbents that do a good job. They're, very, very sophisticated products in the EDA tooling space. Combined enterprise value of over $150 billion. And I was anchoring myself to that, thinking this is the market opportunity, till I realized something else. All of the tooling we use in semiconductors is less than a third of the cost. More than 2/3 is actually the labor, the human cost. And it's even worse. It's more than 2/3 when you can find the engineers to do this stuff. When you can, to your point earlier, Azalia, you can't find 100 physical designers to go do this stuff. And so that's really exciting. Do you view that in the same way? Is the larger opportunity to build the EDA tooling company, or is the larger opportunity to truly sort of automate end-to-end silicon design in a way that you can capture that labor spend as well?
Yeah, absolutely. We think that the end-to-end chip design market is a much bigger opportunity. The way we think of Ricursive is that we are not a tooling company. We build tools as needed to move forward our mission.
Right.
What we want to offer, an end-to-end platform where with AI and with accelerated distributed computing, we take care of all these lengthy, complex, as you said, sequential process for our customers. So we are not just one tool that the customer still needs a large team to play with. Yeah. We are a full kind of package and a platform.
Right. That gives you that opportunity not just to sell sort of seats for some licensed software, but actually to do the work, get it done end to end, which is really exciting.
Like right now, the market is there's internal teams of hundreds or thousands of people. And it still takes a couple years.
Right. And so
Yeah.
you could do it faster, you could do it better, and you could do it end to end for the customers. And that's sort of the dream here. I remember a phrase, parts of this have been happening in the semiconductor market. TSMC came up with the idea of fabless semiconductor manufacturing, where I don't need a fab. I just get all the way to physical design. And at the very end, I was send it to TSMC and they built the chip and sent it back to me. I think in one of our earlier conversations, you'd mentioned this notion of a designless. What does that mean in your mind?
So to us, that would mean a new era where companies didn't need to have dedicated in-house teams of hundreds or thousands of engineers and specialists in order to be able to design their own chips. They could basically outsource that to Ricursive, and they could just, as Azalia said, focus on the application layer. We could build a custom silicon for them, just as TSMC ushered in the fabless era, where companies didn't, like NVIDIA can be $1 trillion company without having its own fab.
And in that scenario, what is the role of an engineer inside those companies at the systems layer, at the hardware layer? What do you believe should their role be, and what should be the role of AI in that sort of designless world?
Yeah, maybe it is a little like the vibe coding of hardware. I think what we need from humans would be an understanding of the trade-offs that matter to them and to their workload.
That's right.
That's what we need.
That's right. I mean, if you're designing a chip and you're trying to figure out, it's a wireless chip, I'm going to put it in a phone. Should I have all the different bands and wireless and Bluetooth? Or for my particular use case of the market I'm going after, I don't need Bluetooth, or I don't need all the different bands because I'm only going to sell in the US or etc. So it's that expression of intent. Like, what should we do? Those trade-offs. But once the trade-offs are made, then waiting for 18, 24 months to just implement that into hardware, that should be a matter of hours to days to weeks rather than what it is today.
Exactly. And I think you were talking earlier about like physical design and why we would focus on it first. So there's interplay between the stages. And like you're suggesting, like maybe there's a certain high-level chip that could be a very amazing like performance boost, but maybe it's not physically possible to build.
Because otherwise you're 6 months into your design, you've done all the verification, which is another 6 months and hundreds of engineers, only to try and lay it out physically on a chip to decide, I can't fit this. The chip itself would be $10,000 and I'm trying to build something for $1,000. You're so right. Like that's so hard.
And the world is moving so quickly too, right?
Yeah.
So you don't want to miss that window.
Yeah.
And at the same time, another opportunity that this fast process kind of enables is the massive design space exploration that we can do. So not only we can be sure that, okay, these designs are actually manufacturable, because we can do these iterations so fast, we can look into a much wider space of different architectural decisions, different ways that we bring in different devices and material into the chip design process. So we are really opening that up for exploring
That's
these
a great
trade-offs.
point. Like, this industry doesn't take risks today because they can't afford it. If they know something works in physical design, you're naturally going to constrain your thinking up front because you're like, I don't want to reset 6 or 12 months of work. But if you can just have this collaboratively back and forth, then you would explore a much broader. I love that. You would explore a broader design space. We should expect to see more innovative silicon, more innovation at the hardware layer thanks to this.
Exactly.
Better performance, yeah.
And performance and efficiencies. You're solving energy issues, you're solving functionality issues, you're solving timing and cost issues. And that's what makes this such a bold vision. And one of the conversations we had internally was around, why would the incumbents not do this? And I was like, this is very different from the idea of a co-pilot that merely changes how I use a particular EDA tool. You're still bound by the constraints, the design constraint that you're placing on yourself. We need to rethink the entire pipeline of how we build semiconductors, build hardware. I'm personally very energized by that. I want to dig into a little bit into the two of you because that's such an intriguing part of the story. I remember reaching out to you, and one thing that struck me was how you were completing each other's sentences. It's just so incredible to have you in the same founding team. How long have you known each other? How do you like to work with each other? What makes you a great founding team to start this journey?
I guess it's been almost 10 years now. So we started on the same day at Google Brain.
Oh, wow.
Yeah.
You started on the same day.
On the same day.
That's awesome.
And then we left Bain on the same day. We joined Anthropic on the same day. We left Anthropic on the same day. We rejoined Google on the same day. We left Google again on the same day. And we started this company together. And this worked. We were at Stanford in parallel too.
Yeah.
So we collaborated at multiple companies or institutions at the same time during this period as well.
Not a surprise you're completing each other's sentences. How do you like to work together? How do you distribute tasks? How often do you consult with each other on things? What's your working style?
I think an interesting aspect of our relationship is we started out as workout buddies. So before we ever worked together, we were, for like 9 months almost, like we just would do workout, like high intensity interval training, like circuit training together.
The two of you are an incredible team. But now you have this responsibility to build an incredible team and drive it to do these great things. What do you look for in the team that you hire? What makes a very successful recursive team member?
I mean, we have a really high bar, I would say. So someone both brilliant and easy to work with. Like we're not willing to compromise on either of those dimensions. And someone who's excited about our mission.
It's a very unique project. You need AI expertise, but also you need semiconductor industry expertise. That can't be a lot of people. How do you find that talent?
I mean, people can learn if they're smart. So for example, with AlphaChip, we hired some like really brilliant people who had never done machine learning before or chip design before, and they made major contributions. So you need a critical mass of the knowledge, like of EDA and AI, like frontier AI models.
Right.
But as long as you have that, you can kind of gradually absorb like really like brilliant, easy to work with people and make them really productive.
Right. When I was building my own businesses, one thing I realized was the team is not just the people who are in the room, but the people who are invested in your success. You know, it's your capital partners, it's your advisors, it's even your champions at your design partners and customer sites. I want to dig into that a little bit more, starting with, obviously, we've had now the privilege to partner with you at this last fundraise, so thank you for that. As you can see, our excitement has no bounds. But how did you think about making that decision on partnering, on picking the right capital partner? I know for a fact you know dirt, so partners who wanted to work with you. How did the two of you make that decision? It's not an easy decision, right? You're making a decision for a very long time.
Yeah.
Why Lightspeed?
So I think we cared about a few dimensions. For example, one is that do we get along with each other? Do we like each other, working with each other? And that was the case. We have very much enjoyed our conversation since the first moment we saw you. Like it was
a good coffee.
I think I watched a podcast of you beforehand and I was like, oh, this, yeah.
And you still make me? Oh my God. That's terrifying.
Yes. And the other piece is, of course, we talked with other founders who have worked with you and they shared their experience of working with you.
And hopefully one thing that struck you was how team-oriented we are. I mean, you met me certainly, you met Ravi, you spoke to founders and heard from founders that work with multiple partners here at Lightspeed. I do think what makes us very different is this really one-team approach. I know for a fact everyone here is so invested in sort of your success. If I was to let them come join me at this podcast, trust me, there'd be a couch full of people who was like, I want to be part of this. And so that's great. But let's keep widening the aperture. So there's the capital partners that you bring on board, the advisors, and then in some sense, the champions inside your customers. Now, this is a very conservative market. How are you finding the companies you want to work with? And how are you finding these innovative folks inside who have an appetite to bring you in and work with you? Has that been hard? Or do you find that, wow, people actually are ready?
I think a lot of companies are very excited to work with us because I think it's time for this like process of designing chips to be disrupted. And they've seen our work on AlphaChip as well. People have actually been like very supportive.
Yeah, I hear even before you left Google, just reading AlphaChip paper, there were customers who were just trying to recreate this on their own. I mean, it looks like there's a lot of appetite in the market for innovation.
Like, for example, MediaTek, after we put out our archive preprint, but before we even published in Nature, they had reached out, they got some intros through cloud. They asked us very detailed technical questions for like 2+ hours. We weren't sure why they were interested in that level of implementation detail. But it turned out they were implementing it themselves, like before we even open sourced it. And then they use it internally to design their chips. I think they design them the widest variety of chips in the world. They have like 30+ tape outs per year, which is super impressive.
Right.
Yeah.
That's incredible. I mean, again, goes on to show, sometimes because we are in this AI wave right now, we think of chips as NVIDIA and AMD and TPU and a few other things. What most people don't realize is there are millions, if not tens to hundreds of millions of chips that have been designed historically. They go in everything. They go in a little light bulb. They go in a mic. They go in a phone. They go in anything that is electronic today. And what I find really intriguing and interesting and energizing is that the impact you're going to have is not just on the TPU team, not just on an AI accelerator, but on everything. Everything is going to have compute inside. Everything is going to have intelligence inside. And what we're building at Ricursive now is going to make that possible. And that's so exciting. I do want to take this opportunity to dig in on two questions. One is, you have a very unique background. You have a very research-oriented background. What advice would you give to other researchers who are energized looking at your journey? What is your advice to them on, should they start a company, and how should they start how should they think about this?
I think AI as a field has really enabled us to enter any and all industries. Just like Anna and I were not chip people, right? We were AI researchers entering the chip design field. This is now possible for many, many other industries. And that's like a huge opportunity. I can't think of any other technology that would enable us to think this way and to be broadly applicable like AI. It's like amazing. Right now, there is this huge opportunity for AI to bring a ton of value to everyday life in all aspects of life. So just like many researchers are very, very excited to add value and have impact, I think this is a huge opportunity and a very special moment in time to kind of like act on it. And this could be starting a new company. This could be joining a company. This could be doing the tech transfer on their research, however they can. But it's definitely a unique moment in time for researchers.
Anna, any advice?
Yeah, I think for me, like what I care about is impact. So if I think I can have more impact by being part of a large company, because maybe you have a certain scale of distribution or resource, then I would do that. But if I think I can have more impact by starting my own company, then that's what I'll do.
I love that framing. I really do. I think it's not about, because sometimes there's this false dichotomy. Should I start my own company? Should I join a large company? It's not about that. It's about what gives you energy. And it's probably impact.
Exactly.
And degrees of freedom and your ability to really exercise that intellectual freedom that you would really want to do as a researcher. And sometimes the right answer might be working with you when you were at Google. Sometimes the right answer working with you at Ricursive. Sometimes the right answer might be I go out and strike out on my own. But I love that. And I love that we're at a point now where researchers whose default path used to be academics or maybe a lab within a larger institution now have at least the opportunity to go and have the kind of impact the two of you are looking to have. So that's awesome. Thanks for sharing. I want to end with just a little bit of dreaming with you, over the next 12 months or so. What's most important? What's top of mind? What do you want to get done over the next, say, year or so?
We'd like to launch our first product. So right now we're focused on the partnerships. We're thinking we have 2 or 3 like early design partners,
right?
Like really focus on like hearing their thoughts on our product, like shaping it to be as useful as possible to these early design partners.
I find it incredible that your product roadmap expands every time we So I'm not sure whether that's good or bad, but hey, in the long term, I love it and I take it. And now we have the resources to execute to that. Mm-hmm. So again, I view that as a good, because I think the industry is voting with their feet. They're reaching out to you. They're essentially asking you to expand the footprint of what you define as your initial product. We have the resources. We have an incredible team already. And this is an open invitation for more amazing researchers and semiconductor executives and technologists to reach out to you so we can build the world's best team at taking on this broad mission. It's so exciting. I'm sure you must be excited. Anna and Azalia, I can't thank you enough. I can't thank you enough for taking the time. I know how busy you are. And so this is deeply appreciated. Your partnership is deeply appreciated. We are huge fans. And so we're looking forward to how you change this industry.
Thank you so much.
Thank you.